This is Anthony giving you another tutorial on using Torch and how it can use machine learning to help us with functions. So today we want to approximate a function, and then after we approximate that function with a multi-layer perceptron, next we want to calculate its derivative with respect to the input variables. Now you might be thinking this is exactly what we've done in the past, but in the past, we've actually performed this operation right here, where we take the derivative with respect to the loss function. But instead of taking it with respect to the loss function, we want to take it with respect to the actual function itself. So this could be interesting because in your calculus class, normally you're given a function, for example, y equals x squared. You're asked to calculate its derivative, which is simply just 2x. And maybe even asked to calculate the second derivative, which is just 2. So how can we approximate these second two functions numerically and get reasonable results using a neural network? So we're going to start out just like we did before, just import a few things, and then let's get coding. All right, so I just copied and pasted some code I'd written earlier, but I'm just going to talk through it so you understand what's going on. So define the mesh function and make it into a torch module. I also define this simple function called makeBatch, which is going to take an input x and just add an extra dimension. I also define a dbatch function, which is going to take in this x value, remove that extra dimension, and potentially detach it. I define this makeMLP function, which is similar to what I've shown in the past, where I tell the number of neurons I want in each layer and the number of layers that I want. And additionally, I'm going to tell it which activation function I want to apply. Then it's going to create my MLP, assuming there's only one channel of input. So it's going to 1 to n, so that's the number of neurons. Then it's going to apply my activation, and then do it n to n linear modules, where n again is the number of neurons. And I'm going to apply my activation. And finally, I'm going to go back down to 1 output. And I'm going to unpack that list into a sequential object to make my MLP and return that. Next, I define this class called stepper, which is pretty similar to the doStep function that I've used in the past. In fact, I'm going to actually make an instance of it called doStep. And the unique thing about this function or this class is that I have this underscore call underscore. So whenever I call doStep without specifying a function, it's going to actually call the call function. So it's going to be very similar to what we did in the past. Now let's go ahead and define our x variables. I'm going to define a function that approximates a simple parabola like we've done in the past. So y equals x squared. I'm also going to have output these other two. Okay, so you can see I've created this function which is just going to output my y, my dy dx, and then the second derivative as well, and return all of those, and just simply plot it here just as a sanity check, and you can see it's working. So let's make our MLP next. Okay, you can see I had to change my x and y into a batch format. Then I can run it through my MLP to get my y prime. If I just evaluate it now and plot what y prime looks like, it's likely going to be a very bad approximation because we haven't trained the neural network yet. So let's just take a quick look at what y prime looks like. Okay, you can see that our MLP, it does not approximate our parabola at all. So this is not really a surprise. We haven't trained our network yet. So let's go ahead and train it using our stepper function. Okay, so I trained my MLP for 300 epochs. Now let's see what it looks like. And let's add a legend. Okay, so you can see it's approximating my true parabola pretty well. So the question now is, how can we get our derivatives with respect to the input instead of this loss function? So to do that, we can use the AutoGrad library, or AutoGrad functionality in Torch. So we first, I'm going to just call my MLP. Next, I want to use the Torch AutoGrad function. So that gave me my dy dx. Now I want to do it again, except for the input to this AutoGrad function is going to be the dy dx. So before we go too far, we should explain what's going on. So if I just look at the documentation, you can see it says computes and returns the sum of gradients of outputs with respect to the inputs. So what are the inputs and outputs? So it says the first argument will be the outputs. So it's this y prime that sum, and then the inputs is going to be this xp. Now it's going to expect the input to be a scalar. So that's why I perform the sum in order to make this work. Now let's find the second derivative. Okay, so we calculated the second derivative. Now let's do some plots to see how well it's approximated the function compared to the analytical true value of this parabola that we know it should be. Okay, so after a few false starts there, we got it working, and we can see the approximation of the function. Some interesting things to note is that when I look at this approximation, it looks pretty good. When I look at the first derivative in the middle section, it approximates it pretty well, but as I get towards the edges at -1 and 1, the approximation of the derivative becomes worse, which is maybe not too surprising since we have nothing that's going to train it to go beyond to something beyond negative or below -1 or above 1. So there's nothing really constraining the derivative to be correct. Let's do something similar for the second derivative. Okay, so we've plotted the second derivative that we obtained from the AutoGrad and also the true second derivative, which is just a constant. And you can see that there's actually quite a bit of variation here. We're going from, we have a domain of about 0.5 all the way up to a little more than 2.25, which is quite a bit of change when we know that the true value is just a constant. So that can be helpful to realize that, as we try to approximate higher derivatives, likely the ability of the simple MLP to approximate it is going to be poor. At the same time, we can be encouraged that at least, this is positive, which can be helpful for determining which direction we're optimizing in. However, in general, we see that this approximation is okay. We can try one more thing, which is just what happens when I perform additional steps and I lower my learning rate. So if I change my learning rate to be a little bit lower, you can see it doesn't really change a whole lot. So more training is not going to help. Maybe something else interesting we could try would be a different activation function. I'm going to try ReLU just to show you why it's not going to work. And if you think about it and what we did last time, maybe you could figure it out. Okay, so the approximation is pretty good. If I take approximation of the first derivative, you can see it's not really smooth. It has some jagged points here, which is pretty interesting, and generally it's significantly worse than with the Misch activation. And when I plot the second derivative, you can see that it's just giving me zeros, which is totally wrong. So if we think about why that is, it's because ReLU is just made up of two lines, one going from negative infinity to zero, and then zero to positive infinity, or the zero to positive infinity has a particular slope. When you take the first derivative of a line, we're going to get a constant, and to take the second derivative will give us zero. So MLPs with ReLU activation are not able to approximate second derivatives very well. So in this video, we showed how we can, when we approximate a function with the MLP, we can then take the first derivative with respect to that function and also the second derivative. This potentially could have a lot of applications for things like differential equations, which we'll talk about in the future. Thank you for watching.